Okay, so we left off at naming compounds in organic chemistry. We were naming alkenes and alkynes, and now we're going to move on to cis-trans isomers. Remember, an isomer has the same molecular formula but a different structural formula. Therefore, their physical and chemical properties are going to be different. So we didn't learn about this in Regents Chem, but there are two different types of isomers. One is called cis, the other is called trans. So let's go and define those first. In a cis isomer, the groups are located on the same side of the double bond. And cis comes from the Latin word on this side. So I guess you can figure out what trans means now. Groups are on opposite sides of the double bond. And trans comes from the Latin word across. So that's where we get the word transatlantic. So you can see in this first example, these groups, which are part of the butene, are on the same side. So this is cis-2-butene. Cis meaning groups are on the same side. 2 is the location of the double bond. Here we have trans-2-butene. And this is just showing you the molecular model. Let's look at a couple of more examples. So let's look at trans 1,2-dichloroethene. All right, so we know it's ethene, so we know that there's a double bond in between the two C's. Trans meaning opposite side, so I have a chlorine here and I have a chlorine here, and this is going to be my H's. And then cis 1,2-dichloroethene. Same thing, except for my chlorines are going to be on the same side. I'm going to give you one other example that involves an aromatic ring. Here we have trans 1,2-dichlorocyclohexane. So let me draw my hexane ring, cyclo, so 6 carbons, and I have a trans, so I have a chlorine 1,2. So it doesn't matter where I put it. I'm going to do this. So wherever I start, this could be my number 1 chlorine right here, and this could be my number 2. So trans meaning opposite, so we have one in the front and one in the back, where cis 1,2-dichlorocyclohexane be the same thing, but they're both on the same side. Okay, those are some examples of cis-trans isomers. Next, we're going to talk about aromatic groups, specifically benzene. Well, benzene is a cyclic unsaturated hydrocarbon. So cyclic because it's circular, unsaturated because it has double bonds, and hydrocarbon because it only contains hydrogen and carbon. So in the first diagram here on the left, they're showing you the planar ring structure. And they're also showing you that all of the bond angles are 120 degrees. The middle structure is showing you the resonance structures. So here you have your double bonds in alternating positions. And the last one is actually the usual representation. This circle in the middle, right here, actually represents the delocalized pi electron system. And what it means is it actually makes it more stable than the opposing unsaturated hydrocarbon. So let's say you had hexene. Hexene, 6 carbons, straight chain, unsaturated. And here you have benzene, 6 carbons in an aromatic ring. The ring structure with the delocalized pi electrons actually makes it more stable. The unsaturated regular hexene, straight chain, would go through a rapid addition reaction, meaning it would break the double bonds, make single bonds, and join a bunch of them together. But benzene, because it's more stable in the ring structure, actually undergoes substitution reactions. So all of the H's that are coming off, like that you see here, okay, are then replaced by other atoms. And you usually need a catalyst to do this, and sometimes that catalyst is aluminum chloride. Okay. In table 22.3 here, you see some more complex aromatic systems, and they're just giving you some examples. So when you have 2 benzenes that are attached to one another, you form naphthalene, which are actually what mothballs are made out of. 3, you see anthracene, which is used for dyes. Then you have phenanthrene, which is also used in dyes and explosives. And then you have one that looks very complex, 3,4 benzyprene, which is active carcinogen found in smoke and smog. Now you don't have to know those. I just wanted to give you some examples, and they are in the textbook. The diagram on the right, I think you are missing, because on my copy I could not see it. So I'm going to actually go through each of these on the next page, because these are important that you understand. So the first one we're going to talk about is benzene with a bromine at adjacent carbons. So we're going to call this the number 1 and number 2 position. So we name this like we would name anything else. We've got 1, 2. We've got 2 of them, and they're the same, so dibromo. and the main structure is benzene. So 1,2-dibromobenzene. Now this is also called ortho-dibromobenzene. And the O for ortho means that you have two adjacent groups or substituents. Okay, now the next one we're going to move, and we're going to skip one. We're going to put a bromine on the number 1, and we're going to put a bromine on the number 3. So as you can surmise, I'm sure, this is going to be 1,3-dibromobenzene. This is also called meta-dibromobenzene. And the meta is when you have two adjacent groups with one carbon in between, or two adjacent substituents. And then we're going to talk about one more. I'm going to draw my bromines opposite one another. Well, that was really bad. So this is going to be 1, 2, 3, 4, 1, 4 dibromobenzene, or it's going to be called para-dibromobenzene. And the para, meaning that groups are opposite one another. Okay, now on the top of the next page you have what kind of looks like a very complex structure, but it's not. I'm going to draw it, and then I'm going to talk about something else first. So I have a CH3, then I have NO2, NO2, NO2. All right, so before I talk about this structure, let me just talk about this one. So we know this is benzene, and we know that if I put a CH3 group here, that this is called methylbenzene. That should make sense to you. All right? But this is also known as, or more commonly known as, toluene. Just like we know vinegar is called acetic acid, and it's also called ethanoic acid. So it has a couple of different names depending on how you're naming it. So I wanted to show you this first because you see this structure in this one. If I take away my NO2s, I've got methylbenzene, or also known as toluene. So I'm going to realize that, and then I'm just going to name everything else. So here, if my methyl is at my first position, 1, 2, 3, 4, 5, 6, then this becomes 2, 4, 6 tri-nitro toluene. Two, 4, 6 tri-nitrotoluene, better known as TNT, or dynamite. So tri-nitrotoluene. And technically, you don't have to say where the numbers are, because if it's tri-nitrotoluene and they're every other one, and the toluene has the CH3 in the number 1 position, then technically you can assume that the others are 2, 4, 6, because it has to be every other one. But I like to write the 2, 4, 6 tri-nitrotoluene. All right, moving on to some other examples on that page. If I had so let's put a nitro group up here and a Br group right here. So assuming that the NO2 is number 1, 2, 3, this would be 3 bromo nitro benzene. Now, this, because my substituent groups, the NO2 and the bromine, are separated by 1 carbon, this could also be meta bromo nitro benzene. Let's look at another example. So right away, looking at this, I know I have toluene, or methylbenzene, and then if I go ahead and put a chlorine here, this is simply 3 chlorotoluene, or it could be meta chlorotoluene. Now, the last thing that I want to show you is when you actually add benzene as a functional group to a straight chain molecule. So here is benzene, right? But when I turn benzene into a functional group, it's called a phenyl group. So when benzene is turned into a functional group, it is referred to as a phenyl group. So here's an example. All right, so we have all single bonds. Let's go back to our naming roots. I have 6 hydrocarbons, so we know that this is going to end in hexane. I have to number from left to right, right to left, so my groups get the lowest numbers. So this is number 2, right? And 4. Now, technically, we have to name, we haven't really talked about this, hasn't come into play. We have to do alphabetical. So chloro comes before phenyl, P in the alphabet. So we would name this 4-chloro 2-phenyl hexane. Okay, you're not going to get anything crazy like this on the test, but I do have to introduce these concepts to you. You have to know the difference between ortho, meta, and para. All right, let's move on. Okay, so let's move on to some common functional groups. This should look very familiar and much like Table R from Regents Chemistry. We have what's called halocarbons. So anytime we add fluorine, chlorine, bromine, or iodine to a chain. So here they have an example of iodomethane. So they basically took, if we were to draw this out, they took methane, which is 1 carbon, and they put an iodine on there. So iodomethane. If I had an F there, it would be fluoromethane. If I had a Cl there, it would be chloromethane. So on and so forth. Alcohols have an OH functional group, and if the functional group is not at the end of the chain, then I have to say where it is. So, for example, this is methanol, so it's simply at the end, but let's say I had 3 carbons and my OH group was here, then this would be 2-propanol, because the 2 is giving me the location of the OH group. The OL ending tells me it's an alcohol. Ethers, remember, have an O in the middle of the carbon chain, and then we look to the left and the right, and we name it. So, for example, in the one that they gave us here, if you look to the right of the group, you see a methyl group. If you look to the left of the group, you see a methyl group. So this is simply dimethyl ether. Now, if I have a methyl group on one side and oh, it doesn't want to erase it. Come on. All right, I'll see what I can do with this then. We'll turn this into a 2 C's on the right. Then I have ethyl methyl ether. Because I have an ethyl group on the right, I have a methyl group on the left, and it is an ether. Remember that the only difference between aldehydes and ketones is the placement of the double bonded oxygen. In aldehydes, it's always going to be at the end carbon, and in ketones, it's somewhere in the middle of the chain. So you don't need any numbers when naming aldehydes. So if it's pentanal, it's simply 5 carbons with a double bonded oxygen on the last carbon. If it's butanal, it's 4 carbons with a double bonded oxygen on the end carbon. If it's a ketone, okay, and it's a ketone other than propanone, because prop is 3 carbons, so you need a minimum of 3 carbons to at least make a ketone, because you have to have an interior carbon. You don't have to tell me the number. You can just say propanone, because you know that the double bonded oxygen would have to be on the interior carbon. However, if it's somewhere else, as in this one, you would have to tell me that this is 2-pentanone, because it's a 5 carbon chain and the double bond is on the second carbon. Remember carboxylic acids or organic acids. The reason why they're sometimes called carboxylic acids is because the COOH functional group is considered a carboxyl group. Your functional group is only going to appear on the end, just like an aldehyde. So you just tell me the prefix. 4 carbons is bute, so the COOH is on the end, so it's butanoic acid. Esters. Esters have that unique C double bond O bond in the middle of the chain, and the reason being is because esters are formed from a reaction between an alcohol and organic acid, and it's a dehydration synthesis reaction, which means that they remove water, an H from one and an OH from the other, the alcohol and the acid, and then the two parts that are left link up to form the ester. Esters give things their smells, perfumes, banana extract, vanilla, all of your bathroom sprays that smell good. Amines have an NH2 functional group. It can move along the chain, so you need to tell by number where it's located, unless of course it's the first one. And the one that is not listed here, but I will mention, is the amide, which has a double bonded oxygen and an NH2 group. And that's the rest of your chain. All right, so let's practice a few of these. We're going to do some more in class. Notice on the first one, you have an OH functional group. So I know that this is an alcohol. I count my number of C's, it's 2, so this is simply ethanol. On the next one, I see a double bonded oxygen on the end carbon. I'm thinking aldehyde, but I also see a functional group off the chain, so I need to number. So this is going to be on the second, so this is going to be 2-methyl, and I have 3 carbons in my main chain, so propanal. So the 2-methyl tells me, I spelled that wrong, the location of the methyl group. Prop tells me my main chain is 3 carbons long. The Al ending tells me that it is an aldehyde. I'm going to, well, I can see this one here. The bottom left is an aldehyde. There's no other functional groups on it. 1, 2, 3, 4. So this is just 4 carbons. So this is simply butanal. The last one, you see an OH functional group on the bottom, and you have your methyl group on the top. I can't circle this, so please circle it on yours. So we know it's an alcohol. My OH group is on the second carbon, so this is going to be 2 for the OH, so we've got 2, and we've got 2 for the methyl, so 2-methyl, 2 propanol. So you have to tell me where the methyl group is, and because the OH group is not on an end carbon, you also have to tell me where that is. All right, let's finish up these examples. This was the one that I added to your list. I have a C double bond O NH2, which tells me it's an amide. There's 2 carbons, so it's ethanamide. On the next one, I see a C double bond OH functional group. That tells me it's an organic acid, 2 carbons, so ethanoic acid. Here I see my benzene ring with the COOH functional group, so this is a no-brainer. This is just benzoic acid. And the last two review esters. I see my C double bond O. The easiest way to name this is look to the right of the O, count your number of C's, you have 2. This is ethyl. It came from the alcohol that was used to form the ester. Look to the left of this O, and I see 3 C's, so this is going to be prop and O8. So this is how you name it. The alcohol gets the YL ending, the organic acid that it came from gets the O8 ending. And looking at the last one here, again, here's my functional group. I look to the right of this O, I see 3 C's, so this is going to be propyl. I look to the left of the O, I see 4 C's, butanoate. The propyl came from propyl alcohol, the butanoate came from butanoic acid. Please note that what is drawn last is named first, and what is drawn first is named last. Okay, now I was going to go ahead and talk a little bit about organic chemistry, and I was going to talk about chirality. I was going to review proteins and carbohydrates and lipids and nucleic acids, and honestly, we don't have to know any of it at this level. If you're going on to nursing, you're going to learn things specific in there, and if you're going on to any type of engineering, pre-med, or anything else to do with chemistry, you're going to be taking organic chemistry, and you're going to talk about this in depth. And there's still a couple of things that I want to do in class. We need to talk about modern materials. We're going to talk about polymers, which are part of organic chemistry specifically. And then I just want to review a few concepts in nuclear. All right, so please watch this before tomorrow's class. We're going to be doing some practice problems, which will evolve into your problem set that will be due at the end of the week.